I want to talk to you about the sun. The sun's behind the clouds at the moment, and magnetic fields. And essentially, if you throw out your understanding of magnetic fields, you can't understand the sun. It's something incredibly interesting in so many different ways. So what I'm going to do is I'm going to go from the very centre of the sun way out to where I say the sun finishes. A lot of people say the sun for them finishes at the photosphere. That's where you can actually see the bright orb. But the sun for me finishes at the helopause. That is where a pause is where it travels from solar dominance to galactic dominance, and this happens out beyond the orbit of Pluto. So the sun's active, producing hot gas up to that direction, and there's a whole lot of unusual tricks, bits of physics which are actually, to be quite honest, beyond me. So the sun is 1,000,000 kilometres across, so we're 12.4 thousand kilometres across, so it's 1,000,000 kilometres. It's about 100 times bigger than the Earth. So if you had a metre ruler, the Earth would be a centimetre, and the sun would be that big, or the sun would be a ball, and the Earth would be a little grey concern to it. And the sun is a large ball of gas. It's pretty much the same primeval mix from the Big Bang, which is 1 part helium and 3 part hydrogen. And I'll get into the Big Bang aspect of that later on. But the important thing is that gas is there, and it's under huge gravitational pressure. Now, in the centre of the sun is the core, the very central point, and there's nuclear fusion happening there. So this is generating about 2 watts per tonne of energy, and it's sort of got the same amount of energy output of a huge compost heap, but a compost heap of an enormous size, is 1,000,000 kilometre across compost heap, is actually so hot that it's actually 5,000 degrees on the surface, but in the very centre it's 15 million degrees. And the first from 0 up to 2/3. Now I'm going to talk about the 1 unit being this photosphere, so it's from 0 to 66%, that 2/3. The sun is a very dense plasma, but it's a plasma which has got a critical aspect to it, is that it from 66 down to 0, it goes from a few hundred, say 100,000 degrees to 15 million degrees. So the temperature increases. Now, generally, if I heat something, if I light a match, the match will balloon up, the hot stuff will rise. If I boil something, I tend to boil something from the underneath, it will rise. So if I heat something up, it will get bigger and then rise. But in this section of the sun, that plasma physics doesn't work. The actual sun hitting at the moment. If it gets hotter, it's actually denser. Now, if it's hotter and denser, it will sink. And so what it's meant is that the inner 2/3 of the sun is like a gooey jelly. Or it doesn't take any shear force, but it doesn't, like it's liquid, it doesn't take a shear force, but it's got no heat mechanism for movement. And so there's no convection in the sun. So the centre of the sun is called a radiative zone. Now, a radiative zone in a liquid or a solid is actually called conduction. So this is one area where astrophysics lets us down a bit. They call it the radiative zone in the centre. It is radiation, but radiation within a solid is like conduction. So if I heat up a stone, the heat gets from the centre of the stone by conducting by light or electrons from point to point. The energy is not carried over a distance, it's carried over a short distance, but again by radiation. And so if I was to get a big stone and heat it up and crash it on the fire and break it apart, I would see that it's very hot on the inside. And so if I sort of got a very hot potato in a microwave oven and put all the heat in the centre, and it cooling outside, that heat would be in the centre, the heat would still be going out. It conducts, and so it takes 1,000,000 years to travel 1,000,000 kilometres, that heat to get out. So if the sun suddenly switched off, we'd get about 1,000,000 years of not knowing, not knowing much is going on, because the heat is slowly going out of it. Now this layer is a solid jelly stuff. So if you imagine, I imagine those acetate, acrylate spheres, those soft spongy beetles, a jelly. It doesn't mix. It's sort of like, say, if I had a tub of jelly and I spun it around and held it, it would just wobble. Right? So it can take sort of pressure waves through it, but it can't take shear waves through it. It's sort of a very interesting aspect of it there. So this is a solid layer. Now just above it, the plasma then goes to a lower energy, lower density, and convection takes over. So it then heats up, and then it moves. The energy suddenly moves very fast away from it. Now just cut to our nearest star, Proxima Centauri, which is 4.2 light years away, or roughly 41 petameters away from us. That's a dwarf star, a red dwarf. So it's so small it actually doesn't have a solid core in it. It's completely convection. It's a star which is completely convection, the way that we would imagine a star. Because it's completely convection, it's moving its material around, refreshing its material around, and so it will, because it's burning slower, per percentage burning slower, percentage years, it'll last longer, but it will last a lot longer, about 100 billion years, compared to our star, which is about 15 or 10 billion years, how you add it up. It will last significantly longer because it's renewing itself. Our star has got this problem that the helium was slowly building up in the centre, very, very slowly, and the hydrogen's been left at the top, and it's slowly, it's probably getting hotter because there's the carbon, nitrogen, oxygen cycle, the CNO cycle, starting to pick up. Slowly, very stable, slow burn. So you've got this solid inner 2/3, and this inner 2/3 is rotating at a different speed to, if you imagine the troposphere, the weather, the solar weather, is the last third of the sun up the top. Now, because it's moving, because it's also moving, it does have a magnetic field. It's got a magnetic field built into it, so magnetic field lines go into it. But because it's not moving, it's got no dynamo mechanism of generating an internal magnetic field in it. It's pretty amazing stuff. So there's no internal magnetic field in it. There may be some magnetic field lines up, but this goes up and it has a shear layer. It's called a tachosphere, tachopause. Pauses means where there's a transition from one to another is the term for pause. But it's got this shear layer, and the layer rotates. The sea, or the atmosphere of the sun, rotates more quickly on the equator, and so it shears past it. So it's like a wind. If you're standing on that, if I had my feet on that plasma type 1 layer, which is no convection, and I stood in the convection area, I feel this huge wind of the layers of the sun, because the sun is rotating far too fast for its belly and rotating a bit too slow at the top. So it's got rotational inertia. The centre is rotating, so you've got the conservation of angular momentum. As it cools, the body cools down. As it shrinks and shrinks, and gets smaller and smaller, it runs faster and faster. As things fall into it, they tend to spin it around. And so you've got the external shell of the sun moving too fast at the top, too slow at the top, and this is sort of like a giant salt, pepper grinder aspect, and this is causing enormous magnetic fields to be generated. You do have a domino effect there, because you then have currents and magnetic fields moving through each other, and this forms a, as it's described before, these huge zeta pinch lightning bolts, and these are so large that they bend and are unstable, but they're so large that they form this mesh, this like a fruit mesh bag of magnetic fields around the sun, and convective zones. So convection doesn't go all over the place. It's hooked up to these zones, which the heat goes up and creates this more current. Now the important thing about this, I suppose, is that there's two aspects of it. Is that this layer builds up, and you got the different rotation, and it's got different rotation speeds. So eventually this netting has got a memory and gets more and more tangled. And after 11 years of spinning, it completely collapses, and there's got a south pole and a north pole. The sun breaks up into many different little pole field regions. The magnetic field becomes chaotic and reorients it. So the magnetic field of the sun swaps every 11 years. A very important aspect of it, and this is associated with the solar cycle. You also have these areas of cooler areas of the sun, the magnetic sunspots. The sunspots were seen very early on in human history, but they do appear in pairs in seasons and equate, and they go around. They take roughly a month to rotate around the sun, but they do appear in pairs, and they're a flux loop, and they are cooler. And to be cool, there's two reasons. There's two aspects of it. One is a more efficient energy transport out. How do you cool something down? Well, and the other thing is you take the flame away from it. So there's two aspects to it. Very intense conduction, collapse of the magnetic field, and a cessation of convective transport, right? And therefore less convective heat, less radiative heat. That they're darker, and it's important that they appear in two. But if you've ever heard high voltage, it vibrates. So there's this vibration of this layer vibrating, and this vibration is equivalent to a microwave oven in terms of creating alphane waves, which generate a huge amount of energy. And so just above this layer, this radiative energy is coupled into the atmosphere of the sun, and so it goes from 5,600 degrees Kelvin. We talk about Kelvin rather than a earthbound temperature of 0 degrees. That's a very earthy temperature. You know, 0 degrees, we can survive underneath it. I'm in trouble, that type of stuff. Kelvin's a little bit different, but this vibration on the surface creates you've got the photosphere, then you've got the chromosphere, and the chromosphere means the colour sphere, and this means that this is the sort of thing that you will black out the sun, and you see this large corona. It's chromosphere, the corona, the crown of the sun. This large area of very hot atmosphere. This hot atmosphere will produce these beautiful colours. It gives the colour in spectroscopic colour of our sun. And this is very high energy particles. And so what happens is that the gas gets heated up, and if you wanted to reduce water, you heat it up. If you want to thin out gas, you heat it up, and if there's no space, it just expands and blows up, and it actually blows the solar wind. And so we have solar winds blowing from our sun. but at two speeds. There's fast speed and slow speed solar wind. So coming from the what is it? From the poles, the slow spin. From the equators, the fast spin. So you've got two mechanisms producing here, two zones, mechanistic zones happening. You've got this fast and slow solar wind. So your solar wind is coming out, but after Earth, you have the slow speed interacting with the fast speed, and you have these shock waves. So your solar wind produces this. Besides this, you've got the solar wind up to about after Earth, and after that, there's this pinwheel of these helical shock waves. It's beautiful going up. So it's not just a solar wind; it's this beautiful solar wind. So these space probes go out a certain amount, and they get, a huge shock wave of polar particles, and then blank. So it's like real. I don't know. It's like my holidays when I was a kid. You'd go out and it'd be absolutely beautiful one day, and it raining the next. So that's out in the solar wind, and so you've got the magnetic wind coming up, and you've got these big zeta pinch arcs. Now, these arcs go out, and they can actually break free of their netting and form a solar prominence, a large, huge bank of radiation, and can easily magnetically fry a lot of infrastructure on Earth. And they talk about magnetic field lines breaking. Now, essentially, magnetic field lines is sort of a mental concept of Faraday. There's the plasma tubes break, and they appear to go along magnetic field lines, which is our construction. So the magnetic tubes break, but the magnetic field lines themselves don't break. They can't break. They must always be a complete circle. Mathematically, they just can't break. Sort of like, oh, there's a gap here. That can't go. But in terms as far as the plasma is concerned, confinement, whatever that is confinement is along a magnetic field line, that goes, it can snap and create a huge magnetic storm that is a magnetic flux, like a magnetic EMF pulse gun. It's sort of like the sun forms a pulse gun. And so our sun is very stable, 11-year cycle. Once, a century goes here, and we have to be relatively lucky because we're a small moving target. It just happens to go off and shoot every once in a while. Every once in a while it does shoot themselves. The satellites can get knowledge of this and maneuver out of the way or turn their stuff away, but in general they are designed to fry. So they've got a certain amount of time up there. Anyway, of course, if the astronauts were up there in the space station during a solar flux, I think that's one of the emergency exits. They're not going to start from the space station if there's a big solar storm happening. I'm not sure on that. And it would have been possibly toast to Neil Armstrong if he was up there in a huge solar storm. So, there's there's a whole lot of stuff produced in the solar wind, magnetically accelerated. So you've got these magnetically zeta pinched plasma tubes. They're vibrating. They create microwave or radio radiation, and so all the suns you see are basically skinned. So if you could sort of imagine taking off the peel off an orange, or you've got a fruit which has got a huge layer, you can peel all the way down, and so these are really naked suns. Their atmospheres moved off them, blown away, whereas a red giant sun like Betelgeuse, or these other large suns which appear to grow to a large stage, well, no, they have just lost their ability to throw away their atmosphere, and so and of course, as you are firing your atmosphere away, you're also you've got an equal pressure pushing down, so your atmosphere will just bleed out into space, so a huge amount of space. And Betelgeuse would be equivalent of you could fly through Betelgeuse quite well. You just fly into it and it would be just a warm red glow. It would be not a heavy plasma. It's not particularly hot. It is high temperature, but the actual energy density is very low coming out of Betelgeuse. So I hope that gives an idea of the Sun. And the Sun is a complex plasma machine with the different plasma transition zones, behavior zones, leading to a structure which creates a shear force, which creates the magnetic fields, which creates the functionality of these fields, suddenly increased magnetic field distance on the surface of it, and then eventually you will that will then convert that magnetic energy into heating of the Sun, and so we get the chromosphere. So the chromosphere burns down, exposing the photosphere. Essentially, all suns, larger suns, appear hotter not because of anything to do with their core. Their core is way underneath it. It's millions of degrees. The actual core temperature is so much different that the difference we see between 5,000 degrees, 10,000, 15 degrees that's completely plummeted. It's an order of magnitude. It's millions of degrees difference. No, the difference is that the bigger suns have more intense magnetic field cropping, and so the bigger suns appear hotter because we see deeper into them. The smaller suns, they're less energetic at eating themselves in, so they eat themselves a bit less. So that's a complex thing to understand about suns and about magnetic fields. Look, thanks a lot for watching. I find it intensely interesting. I found it a while to actually pick through, sort of read an equation, read a paper, and go, oh, what I was taught is incorrect. Like, I was taught that a larger sun has a great degree of thermal nuclear fusion, so it's hot. You know, the heat is in the centre more, so if you're heating something more, the whole thing heats up, and it's just got a natural end to it. So eventually across there, and of course then it was very difficult to teach if you had the syllabus saying this is the story. You teach the Hertzsprung-Russell diagram, and as you began to understand more, it became harder to actually teach a simplified but nonetheless incorrect version of it. So thanks for watching about magnetic fields.